Welcome back, everybody. Let's continue to talk about measures of variability. So far, we've talked about the range, which pairs well with the mode, and we've talked about the interquartile range, which pairs well with the median. In this video, let's talk about the standard deviation. It measures variability by assessing how much each score differs from the mean. So as a measurement of variability, the standard deviation pairs very well with the mean. The standard deviation requires more computation than the range and the interquartile range, but it really gives us a much richer sense of the variability in our data. So don't get lost in the computation. As we're working on this, I want you to have this phrase continuing to go through your head. And that's that the standard deviation tells us, on average, how much the scores differ from the mean. On average, how much do the scores differ from the mean? So in essence, the mean is serving as a baseline. To compute the standard deviation, we go through 3 steps. We first compute what's known as the sum of the squared deviation scores. I usually use an SS to abbreviate that because we normally just call it the sum of squares. It's the sum of the squared deviation scores. The sum of squares is the basis for measuring variability when it comes to the standard deviation. The second step is where we compute what's known as variance. Variance is kind of an intermediate step on the way to computing standard deviation. It measures an average squared deviation score. But we're not really interested in squared deviation scores, so step 3 is where we compute the standard deviation, and it is measuring, as I mentioned before, on average, how much the scores differ from the mean. This page right here does a good job of describing the standard deviation and what it takes to compute the standard deviation, but I'll admit, this page is probably a little bit more intimidating than it really needs to be. So I want you to use it as a reference page, because we're going to learn about the standard deviation by going through a few examples and actually computing it. And along the way, I'll give you much more information about step 1 and step 2 and step 3, and when to use each formula. This might be the first time in this class that I need to say this, but this will happen several times this semester. I'll introduce something to you. It'll look a little bit overwhelming, but you have to give yourself a little bit of time and you have to be patient, because pretty soon it all starts to make sense. And once we go through several examples, it really becomes almost second nature. It becomes somewhat more comfortable. All right, so let's just jump right into it. Of course, like in other videos, I already have things worked out, but we're going to work them out together. You can come back to my worked out examples to check your own work later on. Let's look at this first example. In this first example, we're going to assume that we're dealing with population data. So we don't have much data, but we're going to assume that's from the entire population. And that's because the notation that's used in the formulas and the actual formulas that we use do depend on if we've collected the data from an entire population or from a sample. So in this video, we're going to focus on population data. For this particular example, we're asked to assume not only that it's population data, but we're asked to use the definitional formula for computing sum of squares. And you're going to see that this is what we call the definitional formula for computing the sum of the squared deviation scores. And it's called the definitional formula because you can see just by looking at the formula, by definition, what it's doing. It is summing up squared deviation scores. A deviation score is just a value that's looking to see how much does that score differ from or deviate from the mean. So it's the sum of the squared deviation scores. Let me change the views and we'll work on it together. Most of the work that we need to do to compute the standard deviation is at step 1, simply computing the sum of the squared deviation scores. Here's our data. Let's just assume it represents quiz scores. And all that we need to do is follow this formula right here. So of course it uses summation notation. So let's just remind ourselves how we compute formulas written in summation notation. The first thing we need to ask ourselves is sum up what? What are we being asked to sum up? This formula is saying don't sum up anything until you've taken every single score and subtracted the mean, and then once you found that deviation score, you've squared it. So once I have a column of squared deviation scores, then I should sum it up. So in my mind, I put together a plan. I know I'm going to need to compute the mean. Then I'm going to want to subtract the mean from every single score. That'll be this column right here. And then I'm going to need to take those deviation scores and square them. That'll be this column right here. And once I find a list of values for that column, then I can sum them up. Then I will know the sum of the squared deviation scores, which is the basis for computing variability. It is a basis for computing the standard deviation. All right, well, we know that we need the mean, so just off to the side, let's compute that. Remember, the mean equals the sum of x divided by n. Let's go ahead and find the sum of x. The sum of x equals 10 plus 7 plus 6 plus 10 plus 6 plus 15. So the sum of x equals 54. Using that, let's go ahead and compute the mean. The mean is going to equal 54 divided by n. We have 1, 2, 3, 4, 5, 6 different scores. 54 divided by 6 equals 9. In class, I like to use examples with nice round numbers. That way we're not tripping over the mathematics. So let's see how much every score differs from the mean. From every score, I want to subtract 9. So I'm just going to write those in. And then we'll put the answer right in this column here. 10 minus 9 is 1. 7 minus 9 is negative 2. 6 minus 9 is negative 3. 10 minus 9 is 1. 6 minus 9 is negative 3. And 15 minus 9 is 6. This provides a good time to take a quick break and check our work. If we've done this correctly, if we subtracted the mean from every single score correctly, those deviation scores should always sum up to 0. Let's check. Because the numbers are pretty simple to work with, I'm just going to add up the positive numbers and then add up the negative numbers and see if they cancel each other out. When I add up the positive numbers, I get 1 plus 1 is 2, plus 6 is 8. When I add up the negative numbers, I get negative 2 plus negative 3 is negative 5, plus negative 3 is negative 8. So they cancel out and they add up to 0. You should always check that because that will always come out to 0. And if it does, you know you're on the right track. And it also helps you understand why we are computing the sum of the squared deviation scores. I mean, think about it. In general, all that I really want to find is an average deviation score. Well, look at those deviation scores. They always sum up to 0. How can I compute an average based on a sum of 0? I can't. So how do we deal with this problem? The way we deal with it when we compute the sum of the squared deviation scores is by squaring the deviation scores. So let's go ahead and do that next. 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9, 1 squared is 1, then we have 9 and 36. If we're squaring those values, they obviously always need to be positive. And this makes another important point. Sum of squares is a measurement of variability. What's the least amount of variability that we could have in our data? None. No variability. Could we ever have negative variability? No, we couldn't. So we know when we compute sum of squares, the smallest value we can ever get is 0. That would mean there's no variability in our data. But there clearly is variability in this data, so let's compute sum of squares. At this point, we ask ourselves, do we have a column labeled with what we've been asked to sum up? And we do. So we'll compute the sum of squares. That equals, let's see, 1 and 4 is 5, add 9, you got 14, 15, 24, 24 and 36 is 60. So that's it, my friends. You just computed sum of squares. And I'm going to be saying this all semester long because we're going to be computing sum of squares all semester long in a variety of different contexts. Sum of squares is the basis for variability. Just look at what we're doing there. We are using the mean as a baseline measure. We're trying to figure out how much each score differs from the mean. And that measurement right there, the sum of squares, is the basis for our computation of variability. All right, let's come back to this view. It's a little bit easier to read. You can see that we have sum of squares equals 60. Let's move now on to step 2, where we're going to compute variance. And this is variance based on data from an entire population, so we often just call it population variance. When we're dealing with population parameters, we usually use Greek letters as their symbols. And in this case, the symbol for population variance is sigma squared. Yes, that is a sigma. It's a lowercase sigma. When we compute population variance, we're essentially just computing an average of the squared deviation scores. You can see we're taking the sum of squares, which was equal to 60, and then just dividing by the number of scores. So we're just computing an average of the squared deviation scores. And that's getting closer to what we want. We want to know on average, how much do the scores differ from the mean? Now we're going to find out here in step 2, on average, how much the squared scores differ from the mean. So do you see how computing population variance is kind of an intermediate step to get to where we really want to be with computing the standard deviation? We're almost there, but we're not quite there yet. So that brings us to step 3. We want to compute the population standard deviation. So this is another population parameter. We're computing the standard deviation for the population. And the symbol that we use to denote the population standard deviation is sigma. If we already know sigma squared, it's pretty easy at this point to find sigma. We just need to take the square root of it. So in this case, the square root of 10, which is the square root of our value for variance, equals 3.16. That, my friends, is the population standard deviation. And that tells us, on average, the scores in this data set differ from the mean of 9 by about 3.16. On average, the scores differ from the mean by 3.16. Of course, as that value is smaller, there's less variability in our data. As that value grows larger, there's more variability in our data. Do you see how every single score in our data set was used to compute that standard deviation? As such, the standard deviation tends to be a representative value of variability in our data set. And for that reason and others, the standard deviation will be our default measurement of variability. I've already pointed out to you how closely the standard deviation works with the mean. So it makes sense that when we compute the mean as a measurement of central tendency, the measurement of variability that we put right along with it is the standard deviation. Let me show you a quick example of an article that I published recently with a few of my students from my research methods class. The details of this article aren't important right now. Let me just scroll down to the results section. And you can see right here when we're starting to talk about our data and the results of our analysis, we list a mean and right along with it a standard deviation. Here's another mean and right along with it a standard deviation. Every single place we report a mean, right along with it we report a standard deviation. Let's talk about example number 2. Example 2 also assumes that we have data from an entire population. It's a very small data set, but we're going to assume it's from an entire population. So at step 2, we're going to compute population variance, and we'll use the symbol sigma squared. And at step 3, we'll compute population standard deviation and use the symbol sigma. What's going to differ is that in this example, we're asked to use the computational formula for computing sum of squares. This computational formula and this definitional formula will get you the exact same answer. They are mathematically equivalent. But do you notice that when you look at this formula, we can't tell that we are summing up squared deviation scores? In this formula right here, it's very clear what we're doing. We are summing up squared deviation scores. That's why we call that the definitional formula for computing sum of squares. We call this the computational formula because in the real world, it's actually easier to compute sum of squares using this method. So let's switch views and go through this example together. Like before, let's focus on step 1. That's really where the majority of the work is. And here's our data. Again, we can just assume it represents some quiz scores. Let's see what we're going to actually need. I'm going to need the sum of x squared. So I'm going to need every single score squared and then add up those values. So I'm going to just go ahead and make a column labeled x squared. And I'm also going to need the sum of x, that quantity squared. Just by listing my data, I already have a column labeled x, so we have pretty much everything we need. Let's go ahead and find those squared x values. 5 squared is 25, 3 squared is 9, 2 squared is 4, then we have 16 and 1. Let's find the sums that we're going to need. We need the sum of x, so let's add up this column. 5 and 3 is 8, and 2 is 10, 14, 15. Again, I like to use simple numbers in class so that we're not tripping over the mathematics. Let's go ahead and find the sum of x squared too. 25 and 9 is 34, 38, 48, 54, 55. So that equals 55. Of course, you can use a calculator anytime that you'd like to help yourself out. All right, it looks like we have all of the sums that we need to compute the sum of the squared deviation scores. Let's just put those values into the equation and then solve it. So I'll just build upon this formula right here. We need the sum of x squared. That is right here. It equals 55. So we have 55 minus this fraction. On the numerator, the top part of the fraction, it asks for the sum of x, that quantity squared. Let's just go ahead and compute that real quickly. We know the sum of x. I need the sum of x, that entire quantity squared. So what I need is 15 squared. And according to my hand calculator, 15 squared equals 225. So that equals 225. So in the numerator of that fraction, we have 225. And according to the formula, we need to divide by n. And keep in mind, n is based on 1, 2, 3, 4, 5 different data points. So we're dividing by 5. All we need to do now is simplify and solve that. We've got 55 minus this fraction, 225 divided by 5. I'm just going to use my hand calculator. 225 divided by 5 equals 45. And of course, 55 minus 45 equals 10. So my friends, the sum of squares equals 10. Remember, we need to compute sum of squares in order to compute the standard deviation. So the sum of squares is indeed the basis for computing measures of variability. It is the basis for computing the standard deviation. Once we're done with step 1, we have the majority of the work done. Let's move on to step 2. Remember, for step 2, we're just computing an average of the squared deviation scores. So we simply take 10, sum of squares, and divide by 5. We're computing an average, dividing by the number of values we have. And in that case, we get a value of 2. So population variance, which is symbolized with a sigma squared, equals 2. This value right here for population variance is based on squared values. So one way to think about it is that when we compute the standard deviation in step 3, we're kind of undoing the squaring that we did when we computed the sum of squares. So what we do in step 3 is just take the square root of the population variance that we computed in step 2. So we don't want to know sigma squared, we want to know sigma. So let's just take the square root of sigma squared. In this case, it's the square root of 2. And the square root of 2 equals 1.41. So that, my friends, is our standard deviation in this example. And what that tells us is, on average, these scores differ from the mean by 1.41. On average, these scores differ from the mean value by 1.41. Of course, as that standard deviation value is larger, there's more variability in our data. As that value for standard deviation is smaller, there's less variability in our data. Let's just review real quickly what we've learned. We've learned that in order to compute the standard deviation, it takes 3 steps. Step 1 involves computing sum of squares. We learned that we can compute sum of squares a couple different ways. If we compute sum of squares based on the definitional formula, we'd use this formula right here. But we can get the exact same answer computing sum of squares based on the computational formula, this formula right here. Once we get to step 2, we're computing what's known as population variance. And it's kind of an intermediate step. It brings us closer to computing the standard deviation, but it's based on squared values. It's not really what we want to know. So what we do to undo the squaring that we did in step 1 is compute the standard deviation in step 3. We simply take the square root of the population variance. And when we take the square root of the population variance, what do we have? We have the population standard deviation. And what does the population standard deviation tell us? It tells us on average how much the scores differ from the mean. So it is indeed a measurement of variability. In the next video, I'm simply going to show you how to compute sum of squares based on sample data. Let's talk for a second about some of the things that will change. One thing that's going to change is just the notation that we use. So when we compute sum of squares, we'll still compute the sum of the squared deviation scores, but now we'll compute to see how much each score differs from not mu, which is the population mean, but x bar, the sample mean. They're fundamentally exactly the same thing. They're both means. You'll see that all we're going to change is the notation. And we'll also see some differences in symbols, notation, in step 2 and step 3. Instead of computing population variance, we'll be computing sample variance. Instead of using a sigma squared, we will use an S squared for sample variance. And instead of using a sigma for population standard deviation, we'll simply use an S. Those are some pretty superficial changes. That's going to be no big deal. So we'll handle that in the next video. In the meantime, be safe.